And okay, so there is one last definition that I want to introduce on top of what I talked about last time. Hopefully you saw the video for that. And that is, make sure I'm at a reasonable zoom. It's one definition, analytic. And basically what this means is basically equal to its Taylor series. So we saw, for example, cosine of x. Well, this isn't one example that we did, but 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot, dot, dot. Okay. So no matter what value we put in for x, cosine of x is going to be equal to what we get from the power series. Now, if we look at a different function, for example, 1 over 1 minus x, we saw that this was equal to 1 plus x squared plus x cubed plus dot, dot, dot. But only for values of x between -1 and 1. And so in this situation, we could say it's analytic where it converges, or we could say, we could introduce a slightly refined version of this definition, which is that it's analytic at a point. So x equals some value, let's say c. And what this means is the function is equal to its Taylor series in some region around the point C. So we have some region, C minus delta, C plus delta, where F equals its Taylor series, which I'll write as in the general form. Now we have from this that the Taylor series centered at 0, and it does make a difference where the Taylor series is centered, where it will be analytic. So if we know what we want is that it's centered at that point. There we go. I meant to write C instead of x0. So it's analytic at a point if it's equal to its Taylor series centered at that particular point. And then we get if a function is analytic at every point, then it's analytic. We just say just that it's analytic. So it can be analytic within at a point, within a region, and it can be analytic everywhere. Okay, I just wanted to make sure to get that definition out of the way because I'll use this term. But now we'll start looking at series solutions. So we're going to write x is going to be our independent variable. We had been using t because we were looking at these things as being physical systems and evolving with time. But for the sake of notation, simplicity of notation, we're just going to use x as independent variable, y as the dependent variable, and solutions to the differential equation will be y of x, which we are seeking in terms of a power series. Let's see, a n x minus x 0 n. Now, what kind of differential equations will we be looking at? They'll again be second order linear differential equations, but now we'll have the possibility of having variable coefficients. So the general form of this will be p of x, and we'll use capital P in this form. Second derivative of y with respect to x, which is often customary when we aren't talking about a function. We aren't using t as the independent variable, but we really could just write y prime because it's a function of one variable. Anyway, dy dx plus r of x y equals 0, where p, q, and r are some functions. Now, in mathematical physics, a lot of different situations lead to some certain differential equations that turn out to be very useful in a wide variety of circumstances. So just a few examples. X squared y double prime plus x y prime plus x squared minus nu squared y equals 0, where nu is some constant. This is called the Bessel equation. I don't remember anything about it whatsoever from the times that I had this in my classes, but I seem to remember it coming up in quantum mechanics. How, I don't know. That's a question for a physics class. Okay. There's also the example of 1 minus x squared y double prime. In my defense, I think I took quantum mechanics in 2004, so it's been a while. Minus 2xy prime plus alpha times alpha plus 1, y equals 0. And this is the Legendre equation. Again, a very important one that comes up in mathematical physics. And so in both of these situations, we have coefficients that are not constant. And in fact, we also have coefficients that are polynomials. And so this will make them particularly easy to deal with for the situations that we care about. So what we're going to start off with is working with the situation where coefficients are polynomials. But later on, we'll see that all of these techniques that we'll use will apply to analytic functions in general. Polynomials are definitely analytic because their Taylor series is just themselves. So we can think of this as analytic functions are, polynomials are really nice. Analytic functions are also nice. Taylor series are nice because they basically work like polynomials in a lot of different ways. Okay. Now, an initial step that we do to kind of clean up our equation, because we have one side. Oh, that's another thing to note, is that these are homogeneous. And the reason we're only looking at homogeneous equations is because we're looking for homogeneous solutions. We're looking for a fundamental set. So we already have separately methods for finding particular solutions for non-homogeneous equations. So for this, we are just looking at homogeneous equations. Now, because of this, if P, Q, and R have a power of x minus x0 as a common factor, divide it out. So we'll be able to divide it out of every one of the coefficients, and we'll also be able to divide 0 by it, and that won't change the right-hand side. It'll still be a homogeneous equation. Okay. So that's just an initial cleanup step that we do. And we will see that solutions of these equations very closely associated solutions are, or I should say the behavior of solutions. These are very, it's very closely associated with the behavior of p of x near x0. Okay, so if we have a point x0 such that p of x0 is not equal to 0, then a point like this is called an ordinary point. On the other hand, a point x0 such that p of x0 does equal to 0 is called a singular point. Now, what's the purpose of distinguishing these two situations? Well, this is our first example of the behavior of solutions being closely associated with the behavior of p of x. So if it's actually equal to 0 at x0, then something special happens and we call it a singular point. Otherwise, we'll deal with it in kind of an ordinary way. We'll call it an ordinary point. So we're going to start off with the simplest of these situations. We'll deal with an ordinary point. And we'll also deal with, we'll start off with coefficients that are polynomials. So if we divide through by capital P of x, then we get y double prime. Now the coefficient there is just 1. P of x y prime plus q of x y equals 0. P of x is equal to capital Q of x minus capital P of x, and little q of x is equal to capital R of x minus capital P of x. Basically, we've just got it into the form that we're kind of used to for linear ordinary differential equations. And if x0, let's see, how should I put this? If if x0 is such that p of x0 not equals 0, then well, this is an ordinary point. P of x is equal to capital Q of x over capital P of x is continuous, because we're not dividing by 0, near x0. So some interval around x0, we have that P of x is continuous. So by the existence and uniqueness theorem, a unique solution exists near x0. So in that same interval where we have continuity of little p of x. So that's the nice thing about an ordinary point, is that we have, we can guarantee that we have there's a unique solution, and it will satisfy arbitrary initial condition y of x0 equals y0, y prime of x0 equals y prime 0. Now, if we're near a singular point, then we're going to need, if our initial conditions are at a singular point, we're going to need different methods. So we're gonna deal with that later. For now, we're just going to do ordinary. We're going to seek solutions, like we said before. Y of x is equal to a0 plus a1, x minus x0 plus a2, x minus x0 squared, and so on. The general term will be an, x minus x0 to the n, so on. Of course, we write it in sigma notation like this: an times x minus x0 to the n. And we're going to assume that we have convergence near x0. So assume convergence in some interval within some radius of x0 for rho, greater than 0, not less. Rho greater than 0. So these are the type of solutions that we're going to be trying to find. Now, this might not seem like the best solution. We're used to getting solutions in terms of elementary functions, but dealing with exponentials and logarithms and trig functions and square roots and things like that, these are all elementary functions, but they are in a lot of senses a little bit of a, well, they're not really that much of a pain to deal with. Sometimes in, for example, Calc 2, we would convert these things into power series whenever we had functions in terms of elementary functions, in order to say something about them. And this is because power series are, in a certain sense, really easy to deal with. They're easy to deal with numerically because we know they converge, and so we can just deal with the first certain number of terms until we get convergence to the point that we know that we've got close enough to a solution that we want. They're easy to deal with analytically because if we want to take a derivative or an integral, it's just like taking a derivative or an integral of a polynomial. So in these senses, series solutions are actually quite nice solutions. So the question might be, why don't we start off this class by doing series solutions if they're so nice? And the answer is students usually freak out when they see series. Okay, so how are we going to actually do this? What we're going to do is we're going to, just as a reminder, we can take the derivatives of this solution, of this proposed solution, and we get a1 plus 2a2 x minus x0 plus 3a3 x minus x0 squared plus dot 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 n a n x minus x0, the n minus 1 plus dot dot dot, or let's just say for now the sum from n a n x minus x0 to the n minus 1, and notice that the general term is just the derivative that we would get of the general term for the original series. But now, because the first term was a constant, we're not going to start from 0, we're going to start from 1. Similarly, we will get n times n minus 1, a n x minus x0, the n minus 2. Another example of power series being very nice to deal with. But this time we start numbering from 2, and we don't need to go any further in differentiating this, even though we could, because we're going to, for now, just look at second order differential equations. So what we can do is take these series here and plug them into our differential equation, and then try to figure out what the coefficients should be. It'll give us some relationships between the coefficients when we plug this in. We'll try to figure it out. Okay, that's all the talk that we need to do. Theoretical, it's enough to start doing examples. And the first example we will do is an example where we already know the answer. So that will be nice because we'll be able to check that against our previous knowledge. And we'll do it not in terms of, we won't specify an initial condition. We already know what the solutions of this equation are. The fundamental set is sine of x, cosine of x. And we derive this through perhaps some slightly complicated algebraic reasoning to come to the conclusion that the fundamental set for this was sine and cosine. Now we're going to see how to do it with the power series, though. And you might come to the conclusion that it's a little bit easier. So, because I've scrolled them off the screen, I'll just rewrite y of x is equal to the sum from n equals 0 to infinity, a n x minus x0 to the n. Well, we're going to assume that our initial conditions are given at 0. So we're just going to look at it in these terms. Okay, y prime of x is equal to the sum from n equals 1 to infinity of n a n x to the n minus 1, and y double prime of x will go from n equals 2 to infinity, n times n minus 1, a n x to the n minus 2. So we're assuming that there's some region of convergence around 0, and that allows us to manipulate these things in an algebraic way. And what do we get? Well, if we just plug them into the equation, we get sum from n equals 2 to infinity, n minus 1, an x to the n minus 2 plus sum from n equals 0 to infinity, an x to the n equals 0. So this is a relationship between these two series. Now, in order to combine these two things, I want to get the generic term to be the same thing, and I want to start from 0 instead of from 2. So how can I do this? Well, let me rephrase that. And that's what I want to do in this situation. But in the general situation, what I want to do is have the generic terms be the same so I know what the matching coefficients are. And I want to have the same starting point. It doesn't necessarily have to be 0. But as long as they're the same starting point, we can have some additional terms out to the right or to the left or whatever. But as long as we start at the same point, we can match up coefficients. So that's what I'm going to do. In order to rewrite this, I want this one to be in terms of x to the n instead of x to the n minus 1, and I want to start from n equals 0. So what I will do is I will go ahead and say this one starts from 0. And if it starts from 0, what does n need to be? Well, in order to have the first one be 2, I need n plus 2. In order for the first one to be 1 here, I need n plus 1. It's an easy trick for rewriting this. A n plus 2. I need that n to start from 2. So replacing it, I will get n plus 2. And then replacing n with n plus 2, I get n plus 2 minus 2, which is just n. So in one step, I've done both of my goals. I've achieved both of my goals. Go ahead and copy this one. N equals 0. And now, because of these properties that we talked about before, well, a couple of ways I could go about this. The book is going about it in a slightly different way that I would want to. So let's do my way. We can move this over, subtract this over the other side, and then we have on both sides that the coefficients must be equal to each other, the matching coefficients. It's one of the properties of power series that we had. So what we have is n plus 2 times n plus 1, an plus 2 is equal to negative an. So this is the relationship that we get among the coefficients. Now, if we assume that we start off with, well, actually, I want to rewrite this a little bit. I want to say what n plus 2 is. This is just a little cleanup step that I normally do to make this easier to think about. The way I'm going to think about it is that I'm going to have some initial ANs. And then once I have those initial ones, I want to be able to move on to the next one. So I want to be able to iterate those sequence of coefficients. And so what I'm going to say is this is the next one, and I'm going to write it in terms of the previous one. So this is the thing I want. So that's the thing I'm going to get by itself. I'm going to rewrite it like this. Now, we don't know what the first term is, but we do know the first few terms. Well, at this point, we don't know any terms. But if we knew a term, we would be able to get the 1, 2 up from it. So if we knew 0, we would be able to get 2, and then we would be able to get 4, and then 6, and so on. So we started off with A0, for example, but we wouldn't be able to get the odd ones. We would just have the even ones. So we need to know what A1 would be, and then we'd be able to get A3, then A5, and then A7, and so on. So we'll assume for now that we know A0 and A1, and then we'll write the other ones in terms of this, or at least we'll try to. So what do we get? We get that A2 is equal to negative A0 over 2 times 1, 0, sorry. A4 is equal to negative A2 over 4 times 3, which is negative A0, A0. 4 times 3 times 2 times 1 is A0 over 4 factorial. A6 is negative A4 over 6 times 5. So this is negative A0 over 6 times 5 times 4 times 2 times 1, 6 factorial. And just one more, for the sake of doing it in our head, A0 over 8 factorial. And this continues on. This pattern continues on. The numerator, or the fraction, is alternating back and forth between positive and negative, and the denominators are going by the even factorials. So we see a pattern, but we want to establish that it's true. All right, just one. Cover my mouth so you don't get COVID. We see a pattern, but we want to establish that it's true. So we need to be good mathematicians. We need to give a proof, and the proof will be by what's called mathematical induction. So the first step is we need the base case. And in this case, the base case will be A0 is just equal to A0. We're assuming that we know what A0 is. Oh, what's the thing we're trying to prove, first of all? A 2k, so our even terms are going to be equal to negative 1 to the k over 2k factorial. That's what we're trying to prove. So what do we have for A0? That's going to be negative 1 to the 0 over 0 factorial. Sorry, left out the A0 here. It's important. So this is just equal to A0. So the base case is okay. Now the induction step is to say, let's say we know it for some values. We'll assume that it's true for previous values, and then we'll use that assumption to show that it's true for subsequent values. So how does this work? Well, we take this assumption that we know that we'll assume that this assumption is true for some k less than j, right? We'll assume it's true for some small values of k, and then we'll prove it for all the other ones. So we'll rewrite this in terms of a 2k is equal to, using our rewriting step, or our recurrence relation. Oh, by the way, that's maybe some useful jargon. This is called a recurrence relation because it's recurring in terms of the previous one. So, and this is called an explicit formula. So this is a formula that involves working it out through all these steps until we get up to the one that we care about. This is something where we don't work through all those steps. We immediately jump to our conclusion. Okay, so we would have that this was negative of a subscript 2 minus the previous one. So 2 times a minus 1 would be the previous one, over n plus 2 times n plus 1. And what is this equal to? Well, because we're assuming that we knew it for smaller values of k, and this is now in terms of a smaller value of k, then we can now use the explicit formula. We're assuming for smaller values it's true. So this is a to the, so let's just pull out the minus. Come on. Yes, I know it's a black pen. Thank you. What is it doing? Okay, I'm just going to ignore it. -1 over n plus 2 times n plus 1. This is our induction step. We know it for previous ones. So this will be -1 to the k minus 1, a0 over 2k minus 1 factorial. I wrote over. We know what the n is here. I wrote in terms of n instead of 2k. So 2k times 2k minus 1. So this will be equal to -1 times -1 to the k minus 1. It's just -1 to the k times a0 over, and now 2k times 2k minus 1 times make a mistake. Oh, not 2k minus 1 factorial. 2 times k minus 1 factorial. Okay. So this is 2k times 2k minus 1 times 2k minus 2 times 2k minus 3 times 2k minus 4 and so on. So that's 2k factorial. In other words, well, that's exactly what we were expecting. This. So once we have it for some initial values, then we can show that it's true for the next one, and then we can use that to show that it's true for the next one, and then we can use that to show it's true for the next one, and so on. And that's the induction step. Now, the importance of the base case is that we had to have one to start off with, and that was a0. Okay. So we've proven that this is, we have one solution, so we'll call it y1 of x, and this is equal to the sum from k equals 0 to infinity of -1 to the k, a0 over, let's just do it like this, a0, we'll pull that out, k equals 0 to infinity, -1 to the k over 2k factorial, x to the 2k. Okay. Now we can do the exact same thing for the odds. So if we start off with a1, and we get that, switch to green. A3 is equal to minus a1 over 3 times 2, which is -a1 over 3 factorial. A5 is equal to -a3 over 5 times 4, which is equal to a1 over 5 factorial. And then a7, we will get -a1 over 7 factorial, and so on. And we will conclude from this that a 2k plus 1, so we want the odd ones now, are equal to -1 to the k, a1 over 2k plus 1 factorial. Now we would go through all of the proof in the exact same way. be the same induction, except we're starting from A1 instead of, maybe it's useful to see this. So let's say it's already been proven for small values, then we'll go to proving it for the next value after all of the small values. So if we were to write this, we would get negative a to the 2k minus 1, so that's 2 down, over 2k plus 1 times 2k. And now we assume that we know the formula is true for 2k minus 1 because that's now small enough. And so what we get is negative 1 over 2k plus 1 times 2k times a to the 2k minus 1, which is minus 1 to the k minus 1, a1 over 2k minus 1 factorial. And so, of course, we get the same thing. We get minus 1 to k a1 over 2k plus 1 factorial. Just another example of using mathematical induction, but this time I didn't write out explicitly what all the steps were. Okay. Now, if we look at these odd parts, we get y2 of x is equal to a1 times the sum from, I'm going to do k is equal to 0 to infinity, minus 1 to k over 2k plus 1 factorial x to the 2k plus 1. And putting these two things together, we get y of x is equal to a0, sum from k equals 0 to infinity, negative 1 to the k over 2k factorial x to the 2k, plus a1, sum from k equals 0 to infinity, negative 1 to the k over 2k plus 1 factorial x to the 2k plus 1, which looks something like a0 plus a1x minus a0 over 2 x squared minus a1 over 6, or 3 factorial, x cubed plus so on. Now, of course, we already recognize these two power series. This is the power series for cosine of x, the power series for sine of x. And now a0 and a1 are arbitrary coefficients. Oh, you got Christmas colors going on. So what we have is, of course, our general solution is c1 cosine of x plus c2 sine of x, exactly what we expected. I want to point out something that I didn't point out at the beginning, which was that because these are constants, okay. So our capital P of x in this case was just 1. And so in this situation, every point is an ordinary point. So we have no concerns for where our solutions are valid. Now, they have this nice picture in the book where they show what happens. Let's start off with cosine of x. We saw this was equal to 1 minus x squared over 2 plus x to the fourth over 4 factorial, which is 24, minus so on. They have this nice picture where you can see if you plot cosine of x and then you just plot 1, you see that it matches it perfectly at x equals 0. If this were an in-person class, I would probably be doing this in Desmos or something. But for the first 2 terms, you see it matches pretty closely with the parabola. The first 3 terms, it matches even closer. And as you add more and more terms, you see it matches cosine of x further and further out. It has those oscillations. It's a nice thing to see, but I'm not going to go to the work bringing up Desmos. Okay, so we have our solution. Now, if we didn't already know the solution, we didn't already know what this was, we don't have to go any further. We could say that this is our solution. However, if we noticed this form of the solution as being written in terms of 2 arbitrary constants multiplied by power series, we could have just given these special names. We could have said that this first series, we'll just call C of x, is just something like this. And we'll just give the other name the name S. Kind of spoiling the idea that we're pretending we don't already know what this thing is. We could ask some things about this. For example, one thing that we could find is that C of 0 is equal to 1. S of 0 is equal to 0. We could take their derivatives and see that S prime of x is equal to C of x. And C prime of x is equal to negative S of x. Right, just in terms of the power series, because we know how to take derivatives of power series. It's very simple. And so we get that C prime, or let's say S prime of 0 is equal to 1. C prime of 0 is equal to 0. And then the Wronskian at C of S evaluated at 0 is just the determinant of 1, 0, 0, 1, which gives us 1. And we would have been able to conclude from this that we have a fundamental set of solutions. We could go further and show that these have all the same properties, sine and cosine, and come to the conclusion that they're sine. Just an interesting fact that these functions that we originally thought of as being defined as right triangles inscribed inside of unit circles, things like that, distances associated with those, also arise, or also could have been defined as the fundamental set of solutions to this particular differential equation. It's an alternate definition of sine and cosine that implies all the same things. Okay, I might start on example 2 because we only have about 5 minutes left. And then I'll continue next time. Possibly, if I get time to do it today, a recorded lecture to kind of make up for my debt. But this is the second example. And it is y double prime equals xy. Deceptively simple looking equation. We're writing it in the form that the standard form that we're using, y double prime minus xy is equal to 0. And this is called Airy's equation. Another one that comes up in mathematical physics. So here we have p of x is equal to 1, q of x is equal to 0, and r of x equal to minus x. And again, because there are no points where p of x is equal to 0, every point is ordinary. Now, let's just go ahead and plug what we already know. I won't write them down again, except to just plug them straight into this. We already know what second derivative will be of our proposed solution in minus. Let's go ahead and do the renumbering. We've done this step before. We'll skip it. We'll just go straight to it. N plus 2 times n plus 1 a n x b n plus 2a. We've already seen how to rewrite y double. On the other side, we'll have x times the sum from n equals 0 to infinity of a n x the n. So actually what we get from this is the sum from n equals 0 to infinity a n x the n plus 1. Okay. And now I want to do a rewriting so that I get matching things. So that's going to be a little bit of trouble. How do I want to do this? Let's do it. I want matching powers of n. So what I can do is I can rewrite this thing as a0 plus n equals, well, let's do it in two steps. N equals 1 to infinity a n x the n plus 1. And now rewriting this, a0 plus, now we'll start from 0. And what we'll have is a n minus 1 x to the n. Okay. So we'll have some a0 floating out here on one side. And then matching coefficients up here. To make sure I'm not messing this up. No, I think I got it right. So matching up coefficients, I get n plus 2 times n plus 1 a n plus 2 equals a n minus 1. Now, the subscripts on this are kind of a pain. We want our next term to be in terms of a n. And so what I'm going to do is I'm going to shift all of these indices up by 1. I'm going to have n plus 3 times n plus 2 a n plus 3 equals a n. Okay. And finally, just this little cleanup step that I usually do, a n over n plus 3 times n plus 2. So again, if we have a 0, we can use that to get a 3, and then we can use that to get a 6, a 9, we can use a 1, get a 4, and to get a 7, to get a 10, And we can use A2, get A5, A8, A11, and then we've got all of them covered. So what we're going to need is to determine A0, A1, and A2. Okay, so I'm going to stop it for there now, and we'll come back to that on the next lecture, whenever that may be, at the latest Monday.
Have a good day.
You too.